Hello, I'm Andrew Cooper. I work for Citrix and the XenServer team. I'm also an upstream maintainer in the hypervisor, and today I'm here to talk to you about migration. Now, I realize it's not what it says up there, but we'll see about it in just a while. So, for those of you who don't necessarily know all the history of x86, around about 1993, there was a big problem. There were a whole load of CPUs out and available and all touting brand new features, and no one really knew how to work out what was available to the software. So Intel introduced the CPUID instruction into some but not all variants of the 486 processor, so you've still got some hoops to jump through there. And the purpose was to return information about the CPU. So it takes some parameters, gives some results back, and it's just system-level stuff, CPU-level stuff. The bit that we're going to care about today is the feature information, because that is what's most relevant and, frankly, most fragile when it comes to migration. So the CPUID instruction is unprivileged. It doesn't trap. It's directly usable by user space, and we'll get back to that problem in a moment. So when you're migrating an operating system, it has a few expectations. Now, these expectations have come from the fact that they were developed on native hardware. On native hardware, you boot up, you do a one-time look around the system, and things tend to stay very constant at that point. Nowadays, kernels will binary patch themselves, so things like the stack and clack instructions for SMAP, and various errata workarounds that may be too prohibitive to have in general. User space does exactly the same. glibc now goes to quite a few extents to try and make memset a couple of cycles faster. Alternatively, things like SSL libraries will happily try and use hardware features where available, and audio-video processing is substantially faster using some of the new FPU pipeline stages. So a whole lot of code nowadays relies on being able to look at CPUID, pick the most available, and use it. Migration is not exactly a reboot. It's modeled as a suspend and resume, and as a result, we must not let any of the details change. In particular, any feature that the guest is using must continue to work after it's moved. And therein lies a bit of the problem. So hardware isn't really quite all identical. Specifically, what we need is that every single instruction continues to behave as it did before. All the MSRs that were available, same as before. So features, and this is not an exhaustive list, but features come from various places, and the CPU to start with, but you've got BIOS settings, so a whole lot of firmware can disable features, set lock bits so you can't turn them back on. Microcode version affects features, particularly if you remember the transactional memory, at which point a microcode update took a feature out of the system. And there's a whole lot of choices you can boot Xen with to enable or disable certain features. So as a result, the choices available are quite complicated and not very straightforward. The one big problem we have with customers is they come along and say, I've got 20 identical servers, and they're not. RMA'd hardware is particularly good at coming back with something that's kind of similar to what you had in before, not identical. And if anyone's ever tried to configure more than one BIOS at once, it's a dull, thankless task. It's very, very common for us to see that supposedly identical servers aren't configured identically, and as a result, the feature sets available are different. So what we need to do is to lie to the guests for their own good and try and pretend that some information is there where, or some information is not there where it actually is. And that brings us on to actually lying to guests. So for HVM, it's really, really quite easy. The CPUID instruction traps, and Xen can make up all the lies it cares about, and the VM has the VM gets all of the information Xen wants to see about it. PV guests are a whole lot different, sadly. I said earlier the CPUID instruction doesn't trap, and therefore Xen has no direct control. That's problematic because PV guests are still a fairly common way of doing things these days. So one solution to this that's been present for... Yeah, it's there. I'm getting to that. So one option that's available is the emulated CPUID, where a guest voluntarily traps into the hypervisor and asks for some mistruths. That's great. The software that knows about it can opt in. It gets intermittent use in PV kernels, so the Xen-specific subsystems of Linux, for example, tend to use this, but all the generic systems don't. And it's basically not used by user space at all. Well, there's one bit of user space, the Xen detect utility, but that's not exactly representative. Now, one option that was a little bit great that came in Ivy Bridge processors called CPUID faulting, where Xen can force execution of CPUID to cause a GP fault. This is great, but it's non-architectural and not guaranteed to ever stay with us. And yeah, it would be lovely if that changed. In this case, that starts behaving exactly like HVM guests, which is very useful for us. For all the rest of the hardware, because as everyone knows, customers are always there spending top money on the top processors. Back in the real world, we actually have some legacy hardware to deal with, and CPUID masking is the unofficial way of doing that on older systems. So just like CPUID faulting, this is non-architectural. The only documentation I can find on it is 2 white papers. Nothing else. On AMD hardware, it's implemented in the terms of override MSRs, so we can directly control the exact information reported back from a CPUID call to the entity running CPUID. One thing you have to be careful of is not attempting to advertise features that the silicon doesn't support. So there's a few hoops to jump through there. On the other hand, it does mean you can set the hypervisor bit for PV guests, which I believe Jürgen had some fun with recently. Intel is different. It's an AND mask against the real hardware values, and because things are complicated, there are 7 different MSRs depending on exactly which variation of the processor you're on. So AMD covers the basic and extended feature leaves, which is kind of fine for them. The Intel covers the Xsave leaf as well, and there are a few other random small ones around. Unfortunately, not all feature bits are feature bits, and there are 2 particularly magic areas. The APIC bit and the OSXsave bits are, well, they're not static. The APIC bit is fast-forwarded from the APIC enable MSR. I still don't actually know why you would want to hide that other than possibly working around a buggy version of Windows. But in this case, if we find APIC is not available, we've got to scramble around trying to enable the APIC, at which point the features will magically reappear. OS X save, on the other hand, is different. That is explicitly documented as a user space visible way of finding the value of the control register for OS X save bit. For earlier MMX operations, there's the fx save and fx restore instructions, which are great and usable by user space, but they change their behavior depending on control registers, and there's no easy way for user space to work out what the affected settings are. So this is why OS X save is represented in this way. It means you can easily see what the operating system has set up for you. Sadly, the interaction with these is completely undocumented anywhere. I reverse engineered some of it, and those of you who are keeping up to date with the XenDevel mailing list will find that even as early as Monday, we found some bugs in my reverse engineering. Hopefully it's correct now. I wouldn't necessarily count on it, though. So, along similar lines, there are a number of areas that are just problematic to control. 1 gig superpage support, for example. There's a feature bit for it, but if you ignore the feature bit and set up a 1 gig superpage, it may work, it may not. There's no control register in the paging settings to control whether that works or not, which means we can't actually hide its presence from guests. AES instructions, again, that's just a feature bit for the instructions themselves. There's no control register to enable or disable the use of them. So again, a VM that probes around can find and start using them, and then may get unhappy when it moves to hardware that doesn't have them. This is a particular gem I found whilst redoing some of the CPUID work. It turns out that AMD does actually have support for segment limits in 64-bit. There's a control bit in one of the registers for it, but there's no feature bit. Genuinely don't know how we'd go about signifying the fact that this doesn't exist on some hardware. But as far as I can tell, no one's ever actually used it. I can't find any code that turns this on, so perhaps that's not too much of a problem. Other bits, the FPU pipeline is particularly problematic when it comes here. The MXCSR mask is the control bits to control things like rounding in the MMX pipeline. And the way you grab that piece of information is to execute an fx save instruction and read it out of one of the areas. And that's great, but it may change on migrate. Now, realistically, the MXCSR mask hasn't changed on 64-bit processors until the Xeon Phi, where the set of bits is different, and if you get them wrong, you take a GP fault on the next resume. So if anyone's got a good idea as to how to deal with that, I'm all ears. I think the best we're going to be able to hope for is at least send it with the migrate stream and put a big fat warning on the return side saying this is different, your user space may crash. If anyone's got better ideas, I'm all ears. Other things are the floating point data pointer and the floating point CSDS bits, which are more like anti-features than features. They're new feature bits that indicate that the pipeline has changed behavior, and, well, yes. I'm not quite sure of the point of them. The best you can say is, yeah, it's changed, but software that's relying on that's not going to be looking for the bits, and software that is relying on those will know that they can't rely on them. So that was an interesting challenge, working out how to represent that in the bitmap. So that those we just pass straight through from the hardware and say, sorry, if you're relying on that, tough luck. Other bits are, so three bits here, comp legacy, hyperthread, and x2apic. We can control those in masking. That's fairly easy to do, but they specifically They specifically affect how you interpret other information in CPUID. So as we can't control the other information, we shouldn't control these, otherwise the guest will get even more confused when its topology information looks wonky. Realistically, it doesn't matter too much. They look at it on boot and don't really care thereafter, so it's not actually too much of a problem that, that we can't affect those, but it does make the logic for it a little bit tricky. So CPUID handling in Xen has not seen much love and attention for a long time. The bits to do with controlling a domain haven't changed since the days where there were only single vCPUs allowed. It's got no concept of information. It's got no concept of per core, per socket, per thread information. It also blindly takes what the tool stack says. The tool stack says, here are some bits, and it puts bits in an array and goes and tries advertising those to the guest. But then the problem is Xen comes along later and says, actually, that doesn't look quite right. Here, let's change that and tweak that, and does a lot of runtime post-processing to make some completely unaudited tool stack information look at least somewhat reasonable. There was a huge amount of inconsistencies to do with how the features were advertised and available. Various places used blacklist, various places used whitelist. At least one of the feature leaves was different between PV and HVM guests as to which it did. Some information is still passed straight through from hardware, although luckily it's rather less than it was. One problem that we had, there was a bit of feature dependency logic in there, but it wasn't great and it certainly wasn't consistent. Of course, we know everyone writes perfect code with no bugs in it. And as a result, we get various issues in guests. So there's a glibc bug from a while back where it saw the FMA3 or FMA4 feature and assumed that everything else had been set up appropriately. There was a similar bug around about the same time in the Microsoft C runtime where it saw X2 APIC and assumed that all it saw AVX2 and thought that all AVX had been set up for it. Both of these resulted in user space crashes, and they existed because of a bad dependency logic in the hypervisor where we took out one feature bit and not a dependent feature bit. As a result, you ended up with it was a technically correct, according to the spec, set of features, but it's not a combination that's ever been seen on real hardware, and as a result, no one had ever tested that. There was also no way for the tool stack to work out what was going on. Certainly in the Zappy tool stack, there was a bit of rather hairy logic that tried to execute CPUID and grab some information from the hypervisor and post-process it back into something that looked plausible, except it didn't look plausible. So there's no useful source of information. There is the hardware caps bit of information that's snuck back out of the hypervisor, but that's just an array of bits, and it happens to represent some internal state. And at the time, we didn't even know that was an ABI, and stuff got shuffled, bits got added, synthetic bits got moved around, and as a result, we were exposing a bitmap to user space without any API on it, which is about as useful as it sounds. And it turns out that over 10 years of piling bugs on top of bugs, particularly for DOM0, a whole lot of assumptions exist around the leaked CPUID state that shouldn't have existed. So the C-state, P-state handling in Linux is particularly bad at the moment in this regard. The memory type and range register support for the classic PV kernels is particularly bad. And the tool stack at the moment, well, the control domain, currently relies on leaked information to construct HVM guests properly. So this isn't exactly great. For Zen 4.7, I did a bit of work to try and resolve this. It was work for XenServer, but of course we do everything upstream, so Zen got some nice new features. And the key thing introduced was the feature set, where we expose a bitmap in the API and the ABI. So the keys in that bitmap are as specified in the architecture manual. It's specifically safe to zero extend, which means that the control software can do subset calculations on it without needing to necessarily care about the meaning of the bits. So the toolstack software can easily say, across my node of 1,000 computers, what's the common subset of features, and give that to every single guest. That was specifically the use case we were trying to solve. There are various bits of information that are available. There's the raw feature set, which is straight out of the CPU. There's the host feature set after Zen has decided to apply some of its logic. So various features are turned off on the command line, or various errata workaround, or things that Zen just chooses not to use. So the host feature set is the one that drives most of the logic in Zen, and that is the basis of the CPU has infrastructure, if anyone's familiar with that from Zen or Linux. And the other thing we do now that didn't previously exist is the maximum feature sets for guests. So this is Zen going along and constructing what it will permit as the maximum set of features it will allow, which is good. It gives the tool stack an upper bound on what it thinks it can set, and it also means it's quite easy to get rid of a lot of the runtime logic by just and masking against this. So it removed quite a lot of runtime data manipulation in the hypervisor. The final thing that's there is a bit of Python that writes some C, because we all love stuff like that. There's an algorithm for generating feature dependencies and the code to do that with. In particular, there are some build time calculations, which is great because it turns the runtime logic into O of 1, which is great in the middle of the hypervisor. And it's shared logic between Zen and the tool stack, so there's a consistent view in either part. As with everything, there's still some more work to do. One of the big areas identified was the fact that the feature set's only half of the problem. You need a whole lot more information properly leveled across hosts. So max phys is one in particular. That's the the number of bits on the address bus, which denotes what are valid fields in the page tables, memory type and range registers, a whole lot of that. At the moment, none of that's leveled. If you happen to boot on a larger system and migrate to a smaller one, it might stop working on you. Sorry. The hypercall for policies, I said earlier that there's a set CPUID policy. Whoever did that didn't think it would be a useful thing to get the CPUID policy, so someone needs to implement that. I also want to see about doing policy auditing at the hypercall time. So you provide a policy in the hypercall, run a lot of logic in the hypercall to say, is this a valid policy or not? And if no, you can reject the hypercall. But the result is it means that the cache of information in the hypervisor is definitely correct, and we can drop a whole lot more runtime checking that we are currently doing. Other issues, again, migration. We get back to this. At the moment, the CPUID policy was just something tacked on the side. It gets regenerated from scratch on the destination side. And as we know, no one ever changes an algorithm, so or you always, on any newer version of Xen, you always get the same version back, except when you don't. So in particular, this tends to manifest itself via the first TLB flush breaking after resume, where you've got a write of CR3 and a write of CR4, because that is the first point that Xen actually has the real CPU policy to audit the control register against. At the time that the RAM and the CPU state is in the migrate stream, the tool stack hasn't even considered what it might do for the tool stack, might do for the CPUID policy. So I'm looking to put the CPUID policy in the migration stream and at the head of it, so it's at the start, ahead of the RAM and the CPU, so at least you can audit that as it comes in correctly. And it also allows, at the moment, migration is essentially a one-shot thing. You try it and hope that it doesn't crash on the resuming side. This opens up a possibility for being able to save the first part of the domain without necessarily pausing it and sending that across to the destination saying, can you run a VM that looks like this? And then that will be rather more reliable than presuming that it can run and attempting to deal with that afterwards. And I know that's not strictly part of my talk, but frankly, MSRs is an even bigger pit of woe than the rest of this, so I think I'm going to be busy for a while. Right. Any questions?
So in general, for features which do not have feature bits,
Please don't do that.
well, not in my control, it's internal and but how do you deal with software which makes use of that feature, and how do you deal with by migration or checkpoints to resume?
Hope it doesn't crash.
I think you talked about the pre-migration validation.
Yeah.
And that'd be something that works might have to be added to that to do a check and reject if there was something.
Like there isn't a feature bit, so how do you check?
Well, I mean, we can put various other bits of information in there. So I was thinking having a synthetic feature bit for things like the segment limit enable, that at least says whether the hardware you were running on had it available. Also, things like the MXCSR mask would go in there because it is specific to the hardware and the guest will use it, and there's nothing we can do to control it anywhere else. The best we can do is at least check that it's the same. But yeah, there is no good solution for the features that don't have feature bits. No, it's in the future work section.
So one more question, semantics for the feature set for PB and HBM. Go back to the slide.
Yeah.
So
Yeah. No, that's better.
is PB and HBM by definition a subset of host?
Generally, yes. One of the bits I didn't talk about is that during all of this calculation, if Xen will unilaterally mask out any feature it does not know about, which is an improvement over the previous state where some things were whitelisted, some things were blacklisted, some things were passed through from hardware. So in particular, one of the bugs we had a couple of years ago was that you would migrate from an older version of Xen to a newer version of Xen on newer hardware, and suddenly the sixth feature leaf the new one that Intel introduced was suddenly available and unrestricted to the guest because it was passed straight through from hardware because the software didn't know about it. So that has been fixed now, so any feature that Xen doesn't know about automatically gets stripped out of the mask. So from that point of view, you are only permitting things we do know about, and the advantage there is it means someone has to go and actively patch Xen to add support for a new feature, which means they need to actually at least think about the implications of doing so. They're not quite strict subsets of each other. There's things like the hypervisor bit, where it's a feature you don't see on real hardware, but you are supposed to set for guests. But by and large, for all the functional components of the system, yeah, it is a subset.
Are those configuration values, so that things you configure on the domain, or the host level, or are they computed?
They're computed. So Xen calculates all of this at boot and makes it available to the tool stack. So the tool stack takes the PV feature set and levels that across the pool, and takes the HVM feature set and levels that across the pool. The other thing to say is that PV and HVM guests are different, and there are some features we can support on PV that we can't support on HVM, and there are a lot of features we can only support in HVM and not in PV. It would be nice if the feature bits contained everything, although certainly it's a bit too late on some of them. It would certainly be nice if all new features contained real feature bits in real information, but this is something we're going to have to live with. One gig super pages, so yeah, page table super page. Thank you very much.